Alright, we are ready to start. So again, good evening everybody. We can quickly summarize what we went through last time. We started to talk about systems that are both forced and damped, which means that we have an external force, but we also have a dashpot that provides some damping coefficient to the system. And in order to determine the equation of motion first and then the solution of the equation of motion, which is the response of the system, we went through the same steps that we saw before, which means from the free body diagram, which we actually we don't even have here because it's pretty intuitive. We have only three forces and all the forces are in the same direction. So we can obtain the equation of motion, then we can move to the standard form of the equation of motion. We basically normalize with respect to the mass. In this case, we found out that we have an equation, a differential equation that is non-homogeneous because we have this term here. So this is not equal to 0, but is equal to this external force, which means that our solution will be given by the summation of the solution of the associated homogeneous equation and the particular solution. We started by looking at the particular solution. Again, this is something that is solved with trial and error, so we know that the form, like the general form of the particular solution, looks like this. Once we know this one, we can derive the first time, derive the second time, then we plug here, actually here, here, and here, and then once we plug, we can do a little bit of simplification. In this case, we used like a kind of trick to find the two constants as and bs, because basically we equated to 0 the two terms between parentheses, and then in this case we were able to find our constants as and bs. We should now look at the total solution, which means that we should also look at the associated homogeneous equation. However, we figured out that we can write the equation in this form. When we write the equation in this form, we can kind of separate two components of the solution. One component, which is this one, corresponds to the transient response, and then this other term corresponds to the steady-state response. Now, the transient response is mostly influenced by the damping that we have from the damping and also the elastic constant. The steady-state response is mostly influenced by the external force that we have. Now, with that said, they are both part of the solution, so if we want to be precise, we should consider both components of the solution. However, depending on what kind of situation we are looking at, we may ignore one of the two. In most cases, we ignore the transient response because if the damping is small enough, we can again ignore, or if the timeline that we are studying is long enough, we can see that again in most cases the steady-state response, the transient response becomes negligible with respect to the entire response. So again, with that said, we can focus mostly on the steady-state response. And for the steady-state response, we still have these two constants, x, like big X, and theta, and we can find both the big X and theta as a function of the parameters of the system and of the external force. Because here we have f0, like lowercase f0, we have omega n, we have omega, we have zeta. Same thing here, we have zeta, omega n, and omega. So again, all the parameters of the system and the external force contribute to the amplitude and the phase of this steady-state response. Make sense? Any question? After that, we introduce the concept of frequency ratio, which is the ratio between the frequency of the external force and the natural frequency. If we rewrite the amplitude and the phase after introducing this external parameter, we can find these two functions, again, which are basically the phase and the amplitude normalized with respect to the mass and the elastic constant. We can plot these two functions, and when we plot these two functions, I have to find them again in the textbook, this is what we obtain, which means that we can use again this frequency ratio to have a better understanding of how the system behaves. So here we can see that when we plot the amplitude as a function of the parameter r, here we can see that we have, depending on the magnitude of the of the damping ratio, we have a peak where this frequency ratio approaches 1 as a value. So which means that when the frequency of the external force is equal to similar to the natural frequency, the response of the system increases, which is why we always don't want, for structural purpose, we don't want to have an external force that has a frequency similar to the natural frequency of the system. Because if we have a sudden increase of the amplitude, amplitude of vibration, it means that we have a sudden increase of the strain. If the strain becomes too big, we can go to the plastic deformation. Again, for structural purpose, we always don't want plastic deformation. But even more than that, we can have a complete failure and collapse of the entire structure. So we always want to stay very far away from this value of R. Make sense? We also quickly saw that we can use this for material characterization purpose. We looked at an article where actually these two concepts of frequency and phase of 90 degrees can be used to determine the properties of a certain material. And I think that was the last thing that we saw last time, right? Any question? Alright, if there are no questions, today I would like to go over a problem first. So I would like to see what's going on this system here. Alright, here we have this vertical rod that goes from, let's say, point A to point B, and at the bottom of this rod we have this mass M. Also there is a hinge here that is at this point of the rod. We can call this point O, for example. We know that we have a certain spring here that has elastic constant K, and we also have a dashpot here that has a damping coefficient C. So what we want to do in this case is to find the equation of motion. Also here we have a force, an horizontal force that is applied on the mass, and we know that this force of course changes with time, and we can model this force as F0 times cosine of omega t. So please think about this problem for a couple of minutes to try to figure out how we should approach it. Alright, we are all back, which means we can start to discuss about how to solve this problem. I had a chance to talk with a few students and figure out what we should do. So, any idea from people I didn't talk to in the last 10 minutes? Any suggestion? So, okay, so that's the right approach. So we have to treat this as a rotating body. It is similar to a pendulum. The main difference with like a simple pendulum is that instead of having a rotation with respect to the very top of the body, in the case of the pendulum, here the rotation occurs with respect to this point here. Also, here we have an elastic constant, which of course is going to affect the motion, and we have this external term as well, which is the dashpot, which of course is going to affect the motion as well. And then we have the external force. I see there is a question. Okay, I guess when I started the breakout, no, actually when I joined one of the breakout rooms, I was stopping share, so thank you very much. Okay, so we were saying that we have to treat this system as a rotating body, because this is basically what's going on for this vertical rod. We were saying that the main difference with a pendulum is that the rotation is not occurring with respect to the top of the body, but with respect to a certain point along the vertical direction. And we also have to look at the effect of this spring, the effect of this dashpot, and also the effect of the external force. So what we should do, we should write the summation of moments with respect to point O, we call this point O, equal to the product between the moment, the rotational moment of inertia, and the angular acceleration, which we call with theta double dot. Now I'm going to draw a schematic of the free body diagram. Of course, keep in mind that we are talking about small displacements, which means small angular rotations. For the free body diagram, I'm going to exaggerate this rotation to make easier to distinguish all the distances and the angles. So we have this point that doesn't move, so this will be our, let's say, our pivot point. Let's put it here. Here we have the original direction, and I'm assuming that we are in an instant at which we have a clockwise direction. So let's assume we have something like this. Alright, so here we have our angle theta, which is the angle that we consider for our equation of motion. So what are the forces that are involved in this system? For sure, we have on the very top the force of the spring. If the rod is rotating in this direction, it means that we are stretching the spring, which means that the spring is pulling back in this direction. We can call this F spring. Right. Then the other force that we should look at is the force from the dashpot, which is somewhere around here, and we can call this Fc, for example. Then we have two more forces. One is the force one is the external force, and we know the direction of this force. So this is our F of t, and then the fourth force is the gravitational force. So it goes in the vertical direction, mg. We also know that this force from the dashpot acts in this direction, because if we have that theta is in this direction, it means the rod is rotating clockwise. It means that this force, which depends on the velocity of the bar, is trying to slow down the rotation of the rod, which means it is opposite with respect to the rotation itself. Make sense? Any question about this? So now we have to look at the dimensions. So here we have this distance here, which is L1, like this, again now is in the diagonal direction, the L1. Then we have the other distance, which is this one, L2, again also in the diagonal direction. And then we have the third length, which is between this point and the end, and we called it simply L. So it's this distance here. Makes sense? So now that we have the free body diagram, because we have all the forces and all the distances, since we have to find summation of moments, we can look at the moment of each force with respect to this point here. So we can list them. So let's start with the force from the dashpot, for example. So the force from, the moment generated by the force from the dashpot would be the force itself. So we called it Fc, and then we have this distance here between this force and this point here, which is L2 times cosine of theta. So this angle is theta as well. Also, if we assume that we have like a positive rotation in this way, we will have again, we can assume that our y goes down, our x goes left, so that the positive goes in this direction. So this will be a negative moment with respect to this force here, so we can use the negative sign here. Then we have to consider the force, we have to consider the moment created by the force that comes from the spring. So here we also have the moment of this force with respect to this point is also a negative moment, so we have to use a negative sign. I'm going to put here on the bottom because I don't have space. So we have Fk, and they have to multiply by this distance here, which is L1 times cosine of theta. Then we can look at the contribution of the gravitational force. So the moment of this force with respect to this point is the force itself, it is m times g, times this distance here. This distance depends on this length here, which is simply L sine of theta. In this case we also have a negative sign, because the force of this moment with respect to this force is counterclockwise. So we have a negative sign here. And then we have, what else do we have? We have the external force. So this force also has a moment with respect to this point. In this case the moment is clockwise, which means it's positive with respect to our coordinate system, so we have plus. We can simply call F, or F in this case the distance that we have to look is this distance here, so we have L cosine of theta, and this of course must be equal to m L square times theta double dot. Any question about this? Okay, so far we called the force from the dashpot simply Fc, the force from the spring simply Fk, but we have to express these two forces as a function of the parameters that are involved in the system. So which means that we have to describe this force as a function of the damping coefficient and the velocity, the rotational velocity of the body, which means that this Fc is given by the product between the coefficient of the damping coefficient and the rotational velocity, and the velocity of the body at this point, which means that Fc would be simply equal to c times L2, which is this distance here, times theta dot. This is because what we are doing here, we are looking at the position of this point here, so basically this displacement here, which is which is L2 theta, but since we need the velocity, we have to derive, so we have L2 times theta dot. And of course we multiply this velocity of this point here by the coefficient c, so that we can obtain the force. Makes sense? And then we have to do the same with this term Fk. In this case we don't need to look at the velocity, we need to look simply at the position. So we need to look at the position of this point here, again with respect to the geometric parameters of the body. So we have k, which is the constant of the spring, times L1 times theta. So we're looking at this position here, L1 times should be sine of theta, but since it's a small angle, we consider only L1 times theta. Makes sense? So now that we have this Fc and Fk, we can plug them here and here. So I have, okay, you see from your notes, so we have negative c L2 theta dot times L2 cosine of theta. This was the force from the, this is the moment from the force of the dashpot. Then we have negative k L1 theta L1 cosine of theta. This is the moment from the force of the spring. And then we have minus mg L sine of theta, and then we have plus f0 cosine of omega t L cosine theta equal to the inertia term, which is m L square theta double dot. So we can further simplify this one, because we said small angle, which means that sine of theta is can be approximated as theta. The cosine of theta can be also approximated as 1, again because theta is small, So with these two, what we have, we can simplify, and then we can also rearrange the terms so we can get closer to our standard form. We have m L square theta double dot, so this term here, plus C L2 squared theta dot, plus K L1 squared theta, plus MGL theta equal to F0 cosine of omega t times L. So of course we want to go as close as possible to our standard form, which means that we should put together the terms that have the same derivative of our variable. So here we have theta double dot, here we have one term in theta dot, and here we have two terms in theta, which means we can put these two together, and then we have the non-homogeneous term on the other side. We want to see the standard form, which means that we basically want to divide by the coefficient of the second derivative of the function, so that we can keep theta double dot basically by itself. And in this case, this is what we obtain. So we have theta double dot plus C L2 squared divided by m L squared theta dot plus K L1 squared plus MGL divided by m L squared times theta equal to F0 L divided by m L squared cosine of omega t. Makes sense. So now the equation is in the standard form. Why do we want to have the standard form? Because from the standard form we can immediately determine the natural frequency. How do we determine the natural frequency? For the natural frequency, what we should do is simply looking at the term of our theta. Right. So the square root of this term here is simply the natural frequency. So we have that omega n is equal to K L1 squared plus MGL over ml squared and then square root. Remember that when we want to see the equation in the standard form, we have to divide all the terms of the equation by the coefficient of the theta double dot, which means in this case I didn't divide simply by the mass, but I divided by ml squared. And then when I do this, divided all of them by ml squared, so this theta dot is alone, then this term is finally the square of the natural frequency, which means natural frequency is the square root of this term here. Okay, now I have a question: which natural frequency is this one? These are the units, radians per second, that's correct, but these are the units of which natural frequency? Unfortunately, this doesn't answer the question. At some point, a few weeks ago, we actually started to talk about two natural frequencies. This is the undamped natural frequency. So natural frequency, and then put in parentheses, this is the undamped natural frequency, which means this is what comes only from K. In this case, of course, we have the geometry, basically K and M. As you can see here, we don't have anything about the damping coefficient. But we can actually determine the damped frequency as well. How can we determine the damped frequency? So we know that the relation between damped and undamped frequency is the following, because we have that omega d, which is the damped frequency, is equal to omega n that multiplies 1 minus zeta squared. Do you remember we found this relation between damped and undamped? Now, if we want to find the damped natural frequency, since we already have the undamped natural frequency, we need to determine the damping coefficient. Can we determine the damping coefficient by looking at the equation of motion? Well, we have to be careful, because that formula that you just mentioned is valid only when we have a simple harmonic oscillator that is described by x double dot plus, with the terms that we saw before. What we need now is to look at all the terms of the standard form of the equation of motion, because we know that if we compare this form with the standard form, we know that this term here is 2 zeta omega n, this term here. So what we can do in order to find the damping coefficient as a function of all the parameters of the system, we can take this term here and we can equate this term to 2 zeta omega n. So if we do the following, so we have C L2 squared divided by M L squared equal to 2 zeta omega n, we can simply, take out zeta from here, which will be C L2 squared divided by M L squared times 2 omega n. Omega n is something that we found before, because we found also omega n from the standard form of the equation, which is the coefficient of theta. So we can simply take this term and plug it here, and then we take all this term and we plug it here, so that we can have the damped natural frequency. Make sense? So remember, when we talk about the natural frequency equal to, square root of k over m, again, that is valid only when we have a simple harmonic oscillator. So mass and spring. Okay? When we start to play a little bit with the geometry, or when we have like a rotational body instead of translational body, we have to be careful, because what we have to do is to looking at the standard form of the equation of motion. Make sense? And then compare the standard form of the equation of motion with the equation of motion that we have, where the coefficient of theta double dot is 1, and then we look at the coefficients of theta dot and theta. Make sense? Questions? Okay, I'm going to pause this recording now, and then I will restart, so we can break it down in two pieces.